Hi, my name is Lily Chen. It's my absolute pleasure to present to you my research on automated multi-class detection of diabetic retinopathy using deep learning. Currently, there are over 42 diabetic patients worldwide, and every 1 out of 3 diabetic patients will go on to develop diabetic retinopathy, also known as DR, a common eye disease that can progress to irreversible vision loss without early diagnosis. And in response to that, there have been success with manual screening methods, but they are all time, labor, and cost inefficient. And in response to that, deep learning has found success in the field of DR, but only in binary classification. And while binary classification of DR has achieved high accuracy for moderate or severe cases, multi-classification assessment for DR has been extremely challenging, particularly for early stages, especially the mild stages of DR. And to give you a gauge of the current accuracy for mild cases is about 10%. And thus, there are millions of undiagnosed diabetic patients with DR, and a new solution is needed. Thus, we move on to the purpose of our research, which was to develop a deep learning algorithm that can simultaneously classify 5 classes of DR, especially for early stages and mild stages based off retinal fundus images. And as you can see in the images on the bottom, the progression of DR through the retinal fundus images from without to mild to moderate to severe and to proliferative DR. So now we move on to the approach of how we built this algorithm. So we took over 80,000 training images, 80,000 images from a public access Kaggle database, and we took 35,126 training images and put them through image preprocessing and data augmentation, which we will cover later in the slides. And then we took 85% of that augmented data to train our model. And then we took the 15% of the augmented data to validate our model and tune the hyperparameters. Then we moved on to the testing phase, where we tested with 53,576 testing images, and we evaluated our model with 2 metrics, one with a 5-class prediction and the other with a binary prediction, which served to supplement the 5-class prediction. And we evaluated the 5-class prediction with a kappa score, and we evaluated the binary prediction with the area under curve, sensitivity, and specificity. More about the dataset, as mentioned before, the images for training, validation, and testing were from a Kaggle public access competition, and the label set breakdown was 5 class labels: a normal 74%, mild 7%, moderate 15%, severe 2%, and proliferative 2%. And the training dataset, as mentioned before, there were 35,126 images, and there were 53,576 images in the testing dataset. And we randomly sampled 15% of the images from the training dataset as a validation dataset. So moving on to the image preprocessing. So in this step, we utilize the mean and standard deviation in a module in Keras to standardize the raw features of the raw fundus images in the dataset. And as you can see in the first row, there's a lot of variation in the size, the scaling, the zoom, the fit, the color. And so as part of our image preprocessing, we decided to grayscale these images and standardize the zoom and the fit in order to make the model efficiency more robust and also more efficient and also more accurate. Then we moved on to the data augmentation, where in this step, we generated additional artificial images with techniques such as rotation, reflection, and zoom. And we did this mainly to reduce overfitting in our model, which is extremely significant in this case because we wanted our clinical scanning device not only to perform well in our training stages and with our data set, but also to perform at that same level in new predictions, especially in the clinical setting, to benefit patients and make an impact. And now we move on to the architecture of our model, which was a convolutional neural network. And we have first the input layer where all the retinal images were fed into the convolutional neural network. And then moving on to the convolutional layer where the neurons were able to spot identify the main characteristics inside the retinal images and put them on feature maps, and then the pooling layer where the feature maps were downsampled, and then the fully connected layer where all the neurons were finally connected to the last step to give us the y-hat for the output for the probability before subsequently sorting it into its prediction. And now we give you more details on our convolutional neural network and architecture. So we utilize 10 repeated blocks of convolutional layers, 2 blocks with 50 kernels of size 5 by 5 by 5, and 8 blocks with 100 to 1,000 kernels of size 3 by 3 by 3. And we also incorporated a rectified linear unit as our activation layer, known as the ReLU for its appropriability and speed. And we also incorporated a max pooling layer as well as a fully connected layer with an average of 5,125 parameters across our models, and we implemented this fully with Keras. Moving on to our algorithm training. So we incorporated a distributed stochastic gradient descent as our optimization function for training our neural network weights, and also utilized the RMS prop function as an optimization procedure for hyperparameters. And fully, we trained 10 individual models which differed in parameters and combined their predictions to improve model performance and robustness overall. And for the algorithm evaluation, as mentioned before, we evaluated 2 metrics with a 5-class prediction, also with a binary predictions at various DR severity cutoffs. And this served to supplement the 5-class prediction. And as for the 5-class prediction, we evaluated with 2 metrics with a quadratic weighted kappa and also an accuracy score. And for the binary predictions at various DR severity cutoffs, we did 3 cuts: mild or worse versus no DR, moderate or worse versus no DR or mild, severe or worse versus no DR or mild or moderate. And we evaluated all of these cuts with the area under curve with sensitivity and specificity. So now we come to our 5-class classification results with this data table, and as you can see, on the horizontal is our predicted from our model, as well as on the vertical is the actual labeling, and across the diagonal in the green is the absolute perfect labeling by our model, the perfect diagnoses. And if you take the total of this diagonal green and add it up, dividing it by the entire total of the table, you will get an accuracy score of 0.84, which is extremely significant in this case because it encompasses the mild case in the mild classes in earlier stages and gives us an accuracy rating of 84%. Compared to previous results where a mild class alone was about 10%. So, and also we analyzed the kappa score to analyze and evaluate the association strength of our data, and we found that our kappa score was quite high at 0.81, which was much higher than current and previous research, which were giving us about 0.5 and 0.6. Now moving on to the binary classification results. As you can see, the 3 cuts: mild or worse, moderate or worse, and severe or worse. For mild or worse, the area under curve value was 0.935, moderate or worse was area under curve was 0.931, and area under curve for the severe or worse was 0.955, all above the clinical standard of 0.90, really showing to supplement the effectiveness and also the accuracy of our model, supplementing the 5-class classification results in these binary settings. And now we come to our conclusions. So ultimately, these are the first findings that convolutional neural networks were able to classify multi-classes of DR, especially for early stages and the mild stages. And thus, it improved the accuracy of current systems for detecting early stage DR, revolutionizing the system and also promising a new model for an automated individual and early detection of DR. And furthermore, it accelerates the diagnosis of DR in routine practice to help the assessment and management of patients. And in the future, I can envision this helping millions of patients with early stage DR from proliferating into more dire stages of vision loss. And currently, further research is necessary to determine how and whether this use of this algorithm could lead to improved care and outcomes compared with current ophthalmologic assessment. And for future plans, I plan to put our model and make it more robust through more data sets, and as well as to collaborate with clinicians and have some outreach projects to deploy this algorithm into the community for maximum impact. So thank you so much for listening to my presentation, and have a wonderful day.